Hello y'all, we are Memphis University and today we are going to be doing another calculus done wrong lesson where we wrong calculus before calculus wrongs us. And today is a most exciting day because finally, we are moving past differential calculus, we're moving past derivatives, we're moving past limits, concavity, related rates, optimization, all of those things. And now we are finally entering the second phase of our calculus journey, which is going to be integral calculus. So for the first part of this video, what I want to do is I want to introduce integrals for you, sort of in a basic way. And for the next few videos, we will be talking about integrals exclusively, talking about different aspects of integrals, introducing one by video. So what we're going to do again today is we're going to talk about integrals. So you've probably seen what an integral looks like, even if you didn't know what it meant. So an integral looks like the squiggly S thingy. We're going to have a to b. So these are called the limits of the integral, the lower limit and the upper limit. These will be numbers like 2 to 7. Then you have a function. And then you have this mysterious dx at the end. We're going to be talking about this a lot in our next video when we start talking about limit sums and how integrals are limit sums. But for now, what I want you to know is that whenever you have an integral, there's two things that come in a pair. The integral and the dx, think of it as a sandwich maybe. And what's important actually is the f of x, the meat of the sandwich, as is normal in sandwiches. The meat is the most important part. So f of x matters, and then you squeeze it in between integral and dx. So integral, f of x, dx. You're always going to have them in pairs. And what is an integral? For now, what you want to think about integrals is that integrals are area. When we introduced derivatives as the limits of slopes, even after we started taking derivatives in a harder way, like doing product rule and chain rule and things like that. We will have a lot of hard integrals, but for now, what we want to think about it as is area. So we're going to think about it as area from x is equal to a to b. And what area do we want? We want the area between f of x and the x-axis. So it's the area from between f of x, the function, the graph of the function, and the x-axis. So I have a nice little picture here. Don't be too impressed by my artistic abilities, but I have this generic function f of x, and we have a to b. Is we're going to cut it off. So a and b are very important. Notice that f of x and the x-axis has some sort of region in between it, and that's what we care about. But the region seems to go on forever. So it's important to have this a and b to know what area you're trying to find, to cut off that graph and make this a finite thing. So what we're going to do is we're going to try to find the area of this. Like imagine if this is some sort of field, not the most normal shaped field, but this is a field and you want to find how big this field is. So that's what we're going to try to do. But what you might be wondering is, or what you might be thinking right now is that I have no idea what this field looks like because it's like weird looking, you know, like there's a curvy thing and I'm not going to be able to find this area because I only know how to find the area of very basic shapes like rectangles and triangles and circles. And what I would say to that is that you're right. I don't know the area of this function too. So actually, as I like to do, I'm tricking you. We're not actually going to be talking about integrals mainly in this video. I did trick you. It's okay. Sometimes you get tricked in order to achieve your dreams. I don't know what I'm saying. But today what we're going to do is we're not going to find the area of this guy. We're only going to approximate the area. Approximations are good enough for me. So instead of integrals, we are actually going to be talking about Riemann sums. So don't feel too bad that you're tricked. Sometimes trickers get tricked. Let's talk about Riemann sums. So you might be wondering, what the heck is a Riemann sum? So this video is brought to us by our friend Bernie Riemann from 100 years ago. I don't know math history. He had a famous hypothesis, but none of that matters right now. What we're going to do is we're going to talk about Riemann sums. Riemann sums are the approximation of that area using the most common shapes that we know. We're going to be talking about rectangles mainly. Rectangles areas are really easy, base times height, so we're not going to be able to find the exact area. We're going to approximate it using rectangles because that's an area that we know. Keep in mind that throughout this video, we're going to introduce 4 different types of Riemann sums. We'll introduce them in pairs, left and right Riemann sums, those are rectangles, and then we're going to do midpoint and trapezoidal. Those are the other two types of Riemann sums. But what we're going to see is that there's going to be a common thread as we do all of these videos, as we do all of these Riemann sums, these four types of Riemann sums. The process of each Riemann sum is the same, even if you're doing different kinds of Riemann sums. But all of this is very confusing without an example, so let's start off. So we have this function, x squared, and we have this guy right here. We're going to go from 2 to 8. So 2, 4, 6, 8. So again, our ultimate goal, which will be outside of this video, will be trying to find the area from 2 to 8. Let me just block the work here real quick. So our ultimate goal is to find this area right here, but we're not going to be able to do that yet. Again, that's what the integral will be. But for now, what we're going to do is we're going to approximate it. So we're going to first start off with the left Riemann sum. So first off, we have to determine rectangles. We have to draw some rectangles. And rectangles are, of course, base times height, and those are the important aspects of this rectangle, so we need to find those. So notice we have this guy right here. The number of rectangles is arbitrary. For now, what we're going to do is we're going to have 3 different rectangles. Notice that they'll be the same base, the same length, this guy, this guy, and this guy. Keep in mind that, again, the rectangle number is arbitrary. As you increase the number of rectangles, hopefully you'll see that you'll have a better approximation. So in this case, we are going to do 3 rectangles, so I'm going to call that L3. So let's draw these rectangles. Using the power of technology, we're going to try to use different colors. I have a red marker here, doing too many things with my hand, so I'm not going to be able to open it. Let's see if I can do this. So let's go. So this first rectangle, so I'm going to draw the first rectangle first. So the key as you're doing these Riemann sums, again, is to find the base and the height. So notice that the base is always the difference in the x's. Like, how long is this thing? Well, if you think of this as a ruler, well, it's from inch 2 to inch 4, so this is going to be 2 inches. So the base of this rectangle, I haven't drawn the rectangle actually, of course, but the base of the rectangle is going to be 4 minus 2. And that's the key. Always the base is the difference in the x's. So the first rectangle is going to be 4 minus 2. This is base, and then we're going to multiply it by some height. So it's the base times the height. So for the height, just like the x's determine the base, the height is going to be determined by the y value. And this is where the word left comes in. So what happens is you take the left endpoint of your interval of the base, you go up to the function, and that will be the height. So notice the left endpoint in this case is 2. We're going to go up to our function. That's this point right here, and that's going to be how tall our rectangle is going to be. So notice our rectangle is going to be about this tall. So again, x's determine the base, y's determine the height of the rectangle, and you have to choose a particular y. In this case, we chose the left endpoint, so we plug in 2 into our function x squared to determine this height. So what will be the height? Well, it's going to be 2 squared. Let's write it as 2 squared. And this is the area of our first rectangle. Base, 4 minus 2, height, plugging in 2 into the function to determine how tall this guy is. So we will evaluate this later, but let's draw our second rectangle. So our second rectangle, again, is going to be determined, its base is going to be determined by the difference in the x's. So notice in this case, it's going to be 6 minus 4. So that's going to be 6 minus 4. We can write it as 6 minus 4. If you want, you of course can write it as 2. Then we take this base, and the important thing is now we need to determine how tall this rectangle is. You're going to take this base of this rectangle. Because we are doing left, you take the left endpoint. In this case, the left endpoint of this base is 4. You're going to go up to the function, which is about right here. How you do this is you plug in 4 into this function, so it's 4. So it's 4 squared, and this is our second rectangle. Not the best picture here. So this second rectangle is going to be 4 squared. Great. Again, 6 minus 4 for the base, that's the base. and then plugging in 4 into our function. So it's going to be 4 squared. So let's do our last little guy. Our last guy is going to be 6 to 8. So that's going to be the base of this rectangle, 8 minus 6. Spinning around here, spin, spin, spin. And then for the height of this rectangle, again, because we're doing left Riemann sum throughout this question, we're going to plug in 6 into our function. That's going to be determining our height of our rectangle. It's going to be this tall. 6 into our function, 6 squared. It's going to be times 6 squared. So what we're going to do is we're going to add these up. 3 different rectangles. Base times height, base times height, base times height, where each time the base is going to be the same because it's always the difference in the x's and they're equally spaced. This is not always the case, but in this case it is. 4 minus 2, 6 minus 4, 8 minus 6. And then the height of the rectangle is always plugging in the left endpoint because we're doing left of the base. The actual important thing, the least important thing actually, is just multiplying these numbers correctly. Looks like it's going to be 2 times 4 plus 2 times 16 plus 2 times 36, I believe. 6 squared. Let's see if I can do this. Again, this is the least important part. 8 plus 32 plus 72. That's not too bad. That's going to be 40 plus 72. I believe that's 112. So hopefully this makes sense. Once you start doing Riemann sums, you'll realize that they're actually pretty easy questions. A lot of my students hate all of calculus except maybe Riemann sums because when you're doing Riemann sums, you're always adding and multiplying numbers because it's just base times height a bunch of times. You're adding up a bunch of the areas of rectangles. All you have to do is determine which numbers to multiply and add. Sorry, I lost my train of thought there. So it's always the difference in the x's for the base, and then for the height, it's always plugging in the appropriate point on the base into the function to determine the height. So in this time, we're going to do left. Eventually, we're going to plug in the right, and sometimes we're going to even plug in the midpoint. So let's just do a few more Riemann sums here. Just keep in mind that our goal again was to find the exact area, but now we're just approximating. 112 is a decent approximation. Notice that it's decently close. You're neglecting these sort of parts right here. So I know that my actual area is probably bigger than 112. But that's not the most important thing. Let's practice again, and let's actually do right Riemann sums. So notice it was always the difference in the x's times these y's. Difference in the x's times these y's, where we're doing left. So now we're going to do right. So we have right here. So let's use the red marker to write this, and then we'll draw our rectangles in blue. Crazy how technology has advanced. So we have right Riemann sums. Again, we're going to do 3 because it's arbitrary. Hopefully you can tell that if you did more rectangles, like you have this one right here, and then this one right here, and then this one right here, your approximation would be better and better because your rectangles aren't as fat. You would have thinner rectangles. And what will happen in the next video is we're going to make the rectangles really, really, really skinny. So they're basically lines, and that's what's going to give us the exact area. But for now, we are going to do R3, which is adding up these 3 rectangles for right Riemann sum. So it's not going to be exactly this. Let's try to change markers. So let's do this. So here we go. Again, what we're going to do is we're going to draw our rectangles base times height, where the base and the height are determined by, base is determined by the x's, height will be determined by a certain y value. So in this case, we do have 3 rectangles. The first one still has base 4, so I'm going to mark this out. This is still going to have base 4, not base 4, base 2, 4 minus 2. So it's going to be 2 times something. Then we are going to, instead of plugging in the left endpoint of the interval of the base, we're going to plug in the right endpoint of the base. We are going to be plugging in 4 because we're doing a right Riemann sum. So you take this number 4, notice it's the right side. Sometimes you have to do this O and R thing to determine left and right. That's important, of course. But this is the right endpoint, and what we're going to do is we're going to plug this point into the function. So notice it'll be this point right here, and this is how tall our first rectangle is going to be for right Riemann sums. So it's going to be this tall. How lovely. Notice that in this case, it's above the graph, and that's because the function is increasing. We'll talk about that later. But for now, The base again was 4 minus 2. How tall is this rectangle? Well, you're going to plug in this right endpoint into this function. It's going to be 4 squared. We can just write it as 4 squared for now. But it's still base times height. Height was determined by plugging in the right endpoint into the function. So the next one is going to be 2 times 6 squared, because you plug in the right endpoint of our second rectangle. That's going to be 6. We're going to go up to the function, and then we're going to draw this. So this is my right Riemann sum. Hopefully you can tell that this is a rectangle and not my prettiest rectangle. But it's this guy right here. Base 6 minus 4 as before. But instead of plugging in 4, which we did for our left Riemann sum, we're going to be plugging in 6, because it's the right Riemann sum. So we plug in 6, we are going to get 6 squared. And then finally, we are going to plug in 8 now, because that's going to be our y value for our third rectangle by plugging in 8. 8 is the new right point of this interval, of this base. So we're plugging in 8. That's going to give you this tall. We're going to find the area of this rectangle. Still 8 minus 6, which is 2. And again, we're plugging in 8, so it's going to be 8 squared. Then we have to add up all these things. It looks kind of annoying, but it's going to be 2 times 16, 4 squared, 2 times 36, 2 times 64. Add them up. Looks like you're going to have, we can factor out a 2. So sorry, I'm going upstairs, but it's 2. Again, when you actually multiply and add the numbers, it's the least important thing, because I'm sure that you can multiply and add numbers. But in this case, 36 plus 64, I believe, is 100. So it's going to be 100 plus 16 would be 116. So it looks like we have 232 here. And that's it. So the area is going to be smaller. Sorry, that's not the 2 there. We multiply by 2. So it's going to be 64 plus 36, 100, 116 times 2 is 232. So that's the right Riemann sum. But notice that no matter what we did, depending on left or right, it was still the same process. And that's what we really want to focus on. It's always, 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 always the difference in the x's to find the base times a different y value. If you're doing a left Riemann sum, you plug in the left point, the left endpoint of the base of the rectangle. If you're doing a right Riemann sum, you plug in the right endpoint of the of the base of the rectangle, no matter what you're doing. So now what we're going to do is we might as well introduce the other 2 types of Riemann sums, and then we're going to practice a few more examples. So in this case, what we're going to do is now we're going to do the third type of Riemann sum, which is midpoint. So let's try to erase our picture here, make it a little bit less cluttered. There we can redraw x squared. It's not going to be too bad. So we're redrawing x squared. So this is this. This. So now what we're going to do is we're going to do midpoint instead. So midpoint is going to be M3. Again, we're going to arbitrarily assume that we have 3 rectangles here. 1, 2, 3. And what we're going to do is we're going to draw new rectangles. But again, it's going to be the same process. We're just going to plug in a different y value for the heights. So we have 3 rectangles here. So we're going to have 2 and 4, 4 and 6, 6 and 8. So again, notice that no matter what Riemann sum I'm choosing, the difference in the x's always remains the same. So it's going to be 2 times something. What's going to change is that you plug in the midpoint value of the interval. So what's the midpoint between 2 and 4? That's going to be 3. So that's going to be determined. So you take this 3 number right here, you're going to go up to the function. So it's going to be 3 squared, which is 9. And that's how tall our rectangle is going to be. So it's going to be 2 times 3 squared. So that's our first rectangle. Base, difference in the x's, height, plugging in the midpoint of our base in this context. So then what we're going to do is we are going to take our second rectangle, still going to be 6 to 4 or 4 to 6. So it's going to be 2 times something again. But instead of plugging in 4, which we did for the left Riemann sum, because that's the left endpoint of this base, or plugging in 6, which we did for the right Riemann sum, because that is the right endpoint of the base. We're going to plug in the midpoint value. The midpoint between 4 and 6 is going to be 5. So we're going to plug that into the function. That's 5 squared, I believe. And 5 squared is going to be the height of this rectangle. And then finally, for our third rectangle, same thing. Difference in the x's, so it's still 8 minus 6, which is 2. Left endpoint, we plugged in 6. right endpoint we plugged in 8. This time we're going to plug in 7 because we're plugging in the midpoint of the base. Keep in mind though that even if we're drawing the 7, the base is still too long because the base doesn't matter about what Riemann sum you're doing, blah, 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 blah. So we're going to plug in 7. That's going to be this tall about. This will be how tall our rectangle is. We're good to go. 7 squared. And if you want, you can actually multiply and add these numbers. Again, I don't really want to focus on that, so I'm not going to do that in this case. Again, the focus is on base times height, choosing different values. So this is the third type of Riemann sum. The fourth type of Riemann sum is probably the most difficult one, the one that people have the most trouble with. But notice it will be the same sort of idea. And why do people have the most trouble with our fourth Riemann sum? Hopefully you've copied this down. It's because it's not a rectangle, it's actually a trapezoid, which is why it's called a trapezoidal sum. So we're going to call this T3 instead. Let's erase these bars here because we want to have a clearer picture. So instead of rectangles, we do know the areas of the other shapes, and in this case, we're going to be using a trapezoid. So let's take this first guy right here. We don't need the 7 anymore. We don't need this 3 because that was part of the midpoints. Hopefully you can see this picture. Hopefully it's not too incredibly terrible. But we have 2, 4, 6, 8. Let's redraw this. So you have this. So again, just like with our rectangles, we want to draw our trapezoids, and once we draw our trapezoids, we should be able to we should be good to go. So still, the base of this trapezoid is going to be 2 to 4, and for left we chose 2, for right we chose 4. For trapezoid, what you do is you actually choose both of them, and then you draw a trapezoid. So it's going to be 2 to 4. So I'm going to draw this one right here. I'm going to draw this guy right here. So that's why it's not a rectangle, it's a trapezoid. And what we're going to do is we're going to connect these dots. So this is a trapezoid. Keep in mind that these are sideways trapezoids, so you gotta like have your head like this, you know. But I'm going to call this the base, even though that this is usually called the height, because again, we're like this. But I want to just be consistent with what we talked about from before. The base is always the difference in the x's, so I'm going to call these the heights. So in my case, the area of our trapezoids is going to be the base, just like normal, times the average of the heights. That's the trapezoid formula. What's the average of two numbers? Of course, you add the two numbers up and then divide by 2. So it's going to be h1 plus h2 divided by 2. So let's go in for this. Let's move this formula over here because we need to use it. B equals B times h1 plus h2 over 2. Same thing as the Riemann sum, except this is slightly different. So instead of base times a single height, you're doing base times the average of 2 heights. So let's see what the first trapezoid is. The first trapezoid is going to be 4 minus 2, which is going to be 2 times, and then instead of the the function value on the left endpoint, that'd be left. The function value on the right endpoint, that'd be right. We're going to be multiplying by the average of those two numbers. So we're going to plug in 2. So it's going to be 2 squared plus, and now we're going to plug in 4. So it's going to be 4 squared over 2. So just pause the video if you want. This is the first trapezoid. The difference in the x's times the average of these two function values, the average of the endpoints function values. So 2 squared and 4 squared. So now let's do the second sum. So the second rectangle, or the trapezoid, is going to be from 6 to 4. This is one endpoint, and then the second endpoint is the right endpoint. We're going to draw our trapezoid as so. And so it's going to be the difference in the x's, 6 minus 4. That's why it's this 2. Notice it hasn't changed from left, right, or midpoint. And then what we're going to do is to find the heights of these rectangles. What are we multiplying this 2 by? It's going to be the average of these two things. Plugging in 4, the left endpoint squared, plugging in 6, and finding the average of those two numbers. So it's going to be 4 squared plus 6 squared over 2. And then finally, we have one last one. You're going to be plugging in 6. You're going to be plugging in 8. So it's going to be like this tall or so. not the greatest trapezoid. 6 to 8, so it's going to be 6 squared plus 8 squared divided by 2. I will leave you to actually find this number if you want. The 2's are kind of nice. Trapezoid is not the greatest thing in the world because it naturally introduces fractions, because you're naturally introduced the average of two numbers, which is a fraction. But hopefully you can see that all of these Riemann sums aren't too bad. It's always the difference in the x's times different y values. If you're doing left, choose the left endpoint's y value. If you're doing right, you choose the right endpoint of the interval's y value. If you're doing midpoint, you're doing the midpoints of the base is y value. And then finally for trapezoid, you do the average of the left and right. So that's Riemann sums. Those are the 4 types of Riemann sums that appear on the AP exam. You do want to know all 4 types because they appear equally often. But questions aren't usually presented in this way. They're usually presented as tables. So let's practice some table questions, and then hopefully we will have mastered Riemann sums to the fullest of our ability, or the fullest extent of our abilities, I guess is the phrase. So again, usually the function is not listed out as just x squared, for example. Usually it's in this table. So let's draw a little table here. So we have this table right here. We have x's, we have function values. Let's make arbitrary x's. So in our previous example, the base was always the same because they were equally spaced out, our x's, but they don't have to be. So let's just do 1, 4, let's do 6. Let's add to this table here. We didn't really plan this out. Let's do 1, 4, 6, and let's do 10 here. Function values aren't too crazy. We can do some negative stuff as well. Nothing too crazy here. So we're going to do these values. And what we're going to do is we're going to approximate this integral. So it's going to be 1 to 10. Again, this means the area under f of x using a Riemann sum. And what we're going to do is we're going to do all types of Riemann sums, or at least left, right, and trapezoidal. We won't be able to do midpoint, as we'll see later, but we'll do a midpoint example to finish this off. So first off, let's do L. When they present these questions, they'll tell you what intervals they want. It's always the intervals of the table. So in this case, there's going to be 3, 1 to 4, 4 to 6, and 6 to 10. So we're going to do L3, which is left. We're going to do R3, which is right. And then we're going to do T3, which is trapezoidal. We might not add and multiply the numbers because I don't know how to do math, but we're going to at least set up everything. We'll just leave it as trapezoid because I don't have enough space to write trapezoidal. Trapezoid. Let's get going. So again. It's always the difference in the x's times different y values. So what some of my students like to do is it's always adjacent pairs of the table, so they like to pair them up. So like so. So we're going to take these 2 first, and keep in mind that we're going right to left. We're starting off these, but when we're doing the difference in the x's, it's this number minus this number because it's a number line. So in this case, we're going to have 3 rectangles. So we can just add up these guys. No matter which one we're doing, even if we're doing trapezoids, it will be 3 trapezoids. So the first one, always the difference in the x's. So we're going to not look at this part, we're only going to look at these 2 columns. So the difference in the x's is going to be 4 minus 1, so it's going to be 3. That's the base of this first rectangle. Oh, and keep in mind that some people draw this out, but you'll notice that you don't have to draw it out. Then the height of the rectangle, well, it looks like we have 2 points. We have the left endpoint of the base, and we have the right endpoint of the base. So what we're going to do is, because we're doing L3, we're going to choose the function value, the f value, the y value of the left endpoint. So we're going to multiply this by 2. So this is base and height. Base is always the difference in the x's. Height is the function value of the left endpoint. Plug in 1, you'll get 2, so that's why it's height. 3 times 2. So now let's practice with L3, or the second rectangle. So it's always the difference in the x's. So in this case, it's going to be 6 minus 4, which is going to be 2. Because we're doing left, we're going to look at this interval, take the left endpoint, and choose that function value as our height of the rectangle. So we're going to choose this number right here because it's the function value of the left endpoint of this pair of columns. So it's going to be times -1. It's okay if it's negative. It just means it's going down instead. Finally, for this last one, it's going to be the difference in the x's. Still, it's always the difference in the x's. So it's going to be 10 minus 6, which is 4. And then what we're going to do is we're again multiplying by the left endpoint's y value. So the left endpoint in this case is 6 of this pair. This is left, this is right. So this is 6. 6 times the, we're going to take the y value of 6, is going to be 3. That's going to be as tall our rectangle is. So again, it's 3, 4 minus 1, 2, choose the left endpoint. Then it's 6 minus 4, 2, choose the left endpoint. And then finally, it's 10 minus 6, which is 4, choose the left endpoint. Notice that as we were doing L3, as we were doing left, we did never multiply and use this number 5 because 5 is not the left, 5 is not a y value of a left endpoint because 10 is not a left endpoint of an interval. You would be using 5 if you did another sum, if there was another rectangle there. So it looks like I can actually add these up. It's not going to be too bad. It's going to be 12 minus 2, which is 10. 10 plus 6 is 16. So again, usually the values aren't too crazy. So now, why don't you pause the video, try to do right by yourself. I really believe you can do it. You can do it, you can do it, you can do it. Pause the video. In 3 seconds, I'm going to reveal the answer and try to base it off the left, and you'll see that it's very similar. So 3, 2, 1, let's get going. Hopefully you got it. Let's see if you got it. So let's do right Riemann sum. So again, it's always the difference in the x's, but for now, what we're going to do is we're going to choose the right endpoint's y value. So it's going to be 4 minus 1, which is 3. For the left, we chose the left endpoint's y value, which is 2. In this case, we're going to choose the right endpoint's y value. What is the right endpoint of this pair? It's going to be 4. So we're going to choose that y value, which is -1. So we're going to do 4, 3 times -1. Then what's going to happen is we are going to have this sum now. So it's going to be 6 minus 4, still 2. And then we're going to now choose the right endpoint y value, that's 3. Finally, we have 4. Choosing the right y value again, that's going to be 5. Add up these guys, it's going to be 6 minus 3, that's just 3. 3 plus 20 is 23. So just keep in mind, look at the similarities. It's always the difference in the x's, so it doesn't matter what Riemann sum you're going to do. So that's why this 3 is the same, this 3 is the same, this 2 and 2 are the same, this 4 and the 4 are the same. What changes as you're doing different Riemann sums is the y value, left values, right values. So let's do trapezoidal real quick because it's the same thing, but instead of doing one of these, you just take the average of these two numbers. So for trapezoidal T3, you have 4 minus 1, which is 3. And then we are multiplying, instead of the left y value or the right y value, we're just multiplying by the average of them. So it's going to be 2 plus -1 over 2. Not my favorite number, but what are you going to do? Then for this guy, still, we're going to use the same number because it's still the difference in the x's of this interval. And then we're going to multiply by the average of these two numbers. So it's going to be -1 plus 3 divided by 2. And then finally, still 4 because it's the difference in the x's. That's the base of the trapezoid. And what we're going to do is multiply by the average of 3 and 5. So it's going to be 3 plus 5 divided by 2. But still, difference in the x's times different y's. Difference in the x's times different y's. Difference in the x's times different y's. So in this case, let's actually just finish this off. This 4 and this 2 will cancel, so it's going to be 2. 2 times 8, I believe, is 16. Then these 2's cancel, that's nice. This is going to be 2, 3 minus 1. And then finally, this is going to be a fraction, unfortunately. This is going to be 2 minus 1, that's 1 over 2, that's 3 halves. Let's try to add up these guys. Looks like we're going to get 18. 18 is 36 over 2. So I think the final answer is 39 over 2. And that is our answer. So hopefully you can see that Riemann sums aren't too bad. Just difference in the x's times different y's. But as promised, we do want to do a midpoint practice just so you can see it. Midpoint cannot be done in this table because we don't know the midpoint value in between 1 and 4. So let's erase this guy and let's do a midpoint. To finish off the 4 different kind of Riemann sums. So I'm just erasing real quick. So midpoint, so let's do a second table. So that's going to be doing this. Usually when midpoint is presented, it's like the ones that we were doing previously, where the x's are equally spaced out. They don't have to be, but every time I've seen it on the AP exam, it is. So we have this. Let's take the numbers 1, 3, 5, 7, 9, and let's populate this the y values with random numbers. So -3, 2, 1, 7. Let's not do 7 because that one is 7. Let's do 6, and then let's do 4. So what we're going to do is we're going to approximate this integral using a Riemann sum, a midpoint Riemann sum. So some people think that trapezoidal is the weirdest one, the weird brother out of the 4 Riemann sums, because you're doing trapezoid instead. But in my opinion, actually midpoint is the weird one, because instead of doing pairs, you're actually doing triads or trios, I guess. So instead of having adjacent pairs like we did for the previous ones, when you have these tables, you're actually going to have 3. Everything is going to come in a group of 3 where the midpoint actually matters. So in this case, we're all going to be able to do M2. They usually tell you the number of rectangles. It's going to be 2 rectangles midpoint, because we have one from 1 to 5 and one from 5 to 7. But this shouldn't be too bad. Again, it's always the difference in the x's. So just keep in mind that this is from 1 to 5. So the difference, the base is going to be 4, 5 minus 1. Same thing with the second base, if you want to do that one first as well. 9 minus 5, that's going to be 4. So what we need to do is determine how tall these guys are. Of course, what we're going to do is we're going to plug in the midpoint of the base. So this base goes from 1 to 5, so the midpoint is 3. And we're going to find that y value, and that's going to be the height of a rectangle. So what's the y value? It's going to be 2, so it's going to be 4 times 2. Notice I don't use -3 and 1 because it's not the y values of the midpoint. That's the y value of the left and the right. So the first one is going to be 4 times 2. Same thing for the second one. Difference in the x's, so it's 4. Not going to choose 1, that's the y value of the left one. Not going to choose 4, that's the y value of the right one. We are going to choose the y value of the midpoint. So what's the midpoint between 5 and 7, which are the endpoints of the interval? That's going to be 7. We're going to plug that into the function. F of 7 is 6, so it's 4 times 6. This is not too bad. This is 8 plus 24. This answer ends up being 32. So again, once you master which numbers to multiply and add, it should be good to go. So one last thing I want to talk about is which ones are bigger compared to other ones. Which Riemann sums are bigger when you have a certain fact about the function. So I'm going to erase this guy right here. So we are going to assume that a function f is decreasing in concave up. And what we're going to do is we are going to sort how big the actual integral is, which will be the area. Remember that's what we started off in the very beginning of this video. It seems so long ago. We're going to see what the left sum is, how big the left one is, how big the right one is, and then how big the trapezoidal is. So I'm going to call it T-trap. So just keep in mind that this question appears on the AP exam, sometimes in free response questions where they ask, is the left sum an overestimate or an underestimate of the actual integral, which is the area? And sometimes they even talk about trapezoidal. And these questions are pretty easy. These questions are pictorial. So all you have to do is draw a picture. What I like to do is I like to draw an x-axis. And then I draw a generic decreasing concave up function. So decreasing means the function is going down like a roller coaster, sort of the down slope. Concave up means it's a U, where it's eating the sky. Its mouth is pointed up. So in this case, we have this sort of function, decreasing and concave up. Then what I like to do is I like to fix an interval, call it A and B. And let's take left first. So for left, remember that the base of these are always consistent between left and right and trapezoidal. So left means you go up to the rectangle, determine height, you take the left endpoint, you take that y value, and that's how tall the rectangle is. So it's going to be this tall. So this is left. Let's label this left. For right, we're going to take the right endpoint, which is b, plug that into the function. So it's going to be this tall. This is right. For trapezoidal, you take the average of those two things. So instead of taking the left or the right, you try to connect it. This is not going to be pretty. Let me try to use that different marker here at the very end, sort of movie magic. So it's going to be, let's see if I can do this very carefully. It's going to be this tall right here. This is trapezoidal. And then the actual area was the original line that we drew. That will be the integral. So I'm going to draw that. So it looks like if you're moving down to up, which one is the smallest? Well, the smallest is right because the right endpoint is the smallest. And that's because the function is decreasing. Then the next thing you hit is a. So a is going to be the next thing. Biggest thing, the actual integral. The third biggest thing is going to be t. And finally, the biggest thing is going to be L. Notice that L is dominating all these guys. Look how tall it is. But that's basically it. If you want, you can practice with increasing and connecting it down and things like that. You're going to get variation or permutation of these letters. But hopefully you can see how to sort them. So that concludes the video. It has been a very long video, but we have introduced a very important concept, Riemann sums. What we did throughout the video is introduce 4 types of Riemann sums: left, right, trapezoidal, which is not a rectangle, but that's fine, and midpoint. For every single Riemann sum, the Riemann sum is used to approximate the integral. So what we were doing is we were using basic shapes, rectangles or trapezoids, to approximate the area under a function. In order to do that, for every single one, we did difference in the x's for the base, and for the heights, we plugged in certain y values depending on what Riemann sum was being asked. So for left, we plugged in the left endpoint. For right, we plugged in the right endpoint. For trapezoidal, we plugged in the average of the two left and right, and for midpoint, we plugged in the midpoint. And that's all it was. But Riemann sums, again, are very important, so if you want to continue practicing these, we do, of course, have a Girls Teach Calculus video in the description below. Be sure to check that out, where one of my former students explained this all a lot better than me, probably. She deals with a lot of questions in those table formats, so if you want to practice those, she also has one of these sort questions at the very end of that video, so be on the lookout for that. Check that out if you want more practice. I highly encourage it. But for now, hopefully you did learn about Riemann sums. If this was useful for you in any way, please like and subscribe to our channel. We want to help you guys out as much as possible. Our next video is going to be a continuation of this in a more theoretical sense, where we make these rectangles very, very, very skinny. We're going to be talking about limit sums and how they are related to integrals and how to convert from integrals to limit sums. So until then, thanks again for watching just like normal, and I hope to see you soon.